This is the 12th video in a series devoted to differential equations. And for the past few videos, we've looked at solving second-order linear differential equations with constant coefficients. And in the last video, we looked at something called the method of undetermined coefficients to solve such differential equations where the forcing function was of the form e to the kx times p of x, where by p of x, I mean a polynomial. And so today we want to up that a little bit and look at more general forcing functions, but not completely general, just another class of forcing functions. In particular, we'll be able to solve differential equations ay double prime plus by prime plus cy equals e to the kx times p of x cosine omega x plus q of x sine omega x. And this is, of course, where p and q are polynomials. But first, we'll look at the special case when k equals 0, which means e to the kx equals 1, which really means we just have polynomial combinations of this cosine and sine. So let's maybe start with the following observation, which we'll sketch a proof of, and that'll set up a solution strategy for solving these kinds of things. And that says, for all natural numbers n, the nth derivative of a of x cosine omega x plus b of x sine omega x is of the form a naught x cosine omega x plus b naught x sine omega x, where a and b are polynomials and a naught and b naught are different polynomials, where the maximum of the degree of a naught and b naught is the same thing as the maximum of the degree of a and b. So in other words, we have some sort of behavior that when we take any order of derivative of an object like this, we end up with another object like this. And we can actually sketch a proof of this quite easily by just looking at a single derivative of a power of x times cosine and a power of x times sine. So let's do that. So if we take a single derivative times x to the k cosine omega x, let's see what we get. So we of course have to use the power rule. So taking the derivative of the x to the k part first, we get k x to the k minus 1 cosine omega x. And then taking the derivative of the cosine part will give us something like minus omega times x to the k sine omega x. And now let's notice that here we've got cosine times x to the k, and here we have a combination of cosine and sine, and the highest degree term we see is this x to the k term. So that motivates part of what we're seeing up here. The other part can be motivated by taking the derivative with respect to k, or the derivative with respect to x of x to the k times sine of omega x. So using the same power rule, we get k times x to the k minus 1 sine omega x plus omega x to the k cosine omega x. Great. So again, the highest power of x we see over here is the same thing as the highest power of x we see over here. Now, given the fact that a function of this form can be written as linear combinations of objects like this, we see that taking the derivative of something of this form will not change its shape. So if taking a single derivative will not change its shape, then taking n derivatives will also not change its shape. So that motivates the following kind of companion observation down here, which will tell us how to solve our upcoming differential equations. And that is, if we have y equals a of x times cosine omega x plus b of x times sine omega x, then if we take ay double prime plus by prime plus cy and do that combination, what we'll end up with is something of the same form. The polynomials will of course change, but the general shape will be the same. So I'll write this as p of x times cosine omega x plus q of x times sine omega x. So let's write then, so if y is of that form, then ay double prime plus by prime plus cy is of this form. And that motivates us to write down a pretty easy theorem which gives us a strategy for solving these types of differential equations in our special case when k is equal to 0. And that's what we'll start the next board with before we look at some examples. So far we looked at a couple of calculations that motivate the following theorem, which will help us solve a certain family of second order differential equations. So what we have here is the particular solution of this differential equation ay double prime plus by prime plus cy equals p of x cos omega x plus q of x sine omega x, where p of x and q of x are polynomials, is of the form y sub p, which is equal to a of x cosine omega x plus b of x sine omega x, where we can also say something about the degree of the polynomials a and b. So if cosine omega x and sine omega x are not solutions to the companion homogeneous differential equation, then the maximum degree of a and b is the same as the maximum degree of p and q. Whereas if the cosine omega x and sine omega x are solutions to the companion homogeneous differential equation, which means it actually simplifies to the following form, then the maximum of the degrees of a and b are one more than the maximum of the degrees of p and q. Okay, so now that we've got this written down, let's see maybe how we can use this. And we'll do that starting with a fairly simple example, which is y double prime minus 2y prime plus y equals cosine of x plus 3 times sine of x. So let's first look at the companion homogeneous differential equation, because we'll need that to have a general solution in the end. So the homogeneous differential equation will be y double prime minus 2y prime plus y equals 0. And let's notice that has an associated polynomial of r squared minus 2r plus 1 equals 0, which factors to r minus 1 quantity squared. But that means we have a double root. But since we have a double root, we can write down our homogeneous differential, or our homogeneous solution as follows. So I'll call it y sub h is equal to c1 plus c2 times x times e to the x, where c1 and c2 are arbitrary constants, which would be fixed if we indeed had initial conditions, but we don't in this case. Okay, so we've got a solution to the homogeneous part. Now let's look for our particular solution, which by our theorem, we have an idea of its shape. So in this case, we've got just a constant times cosine and a constant times sine, so we can think of those as degree 0 polynomials. So that means our solution should also be a constant times cosine plus a constant times sine. So we've got yp should hopefully be of the form a times cosine of x plus b times sine of x, where now a and b are only just real numbers. Okay, so now what we'll do is take the derivative, the second derivative, we'll impose this condition of it being a solution to our differential equation, and hopefully get some sort of conditions on a and b. Okay, so anyway, let's get to it. We've got yp prime is equal to minus a times sine of x plus b times cosine of x. So that's using just the standard derivatives of sine and cosine. And then yp double prime is equal to, let's see, we'll have minus a times cosine of x. And then next we'll have minus b times sine of x. And now let's look at yp double prime minus 2yp prime plus yp. And I wrote it in this different order here because if we notice, we can group these two together and they'll cancel out. If we sum yp double prime and yp, that just gives us 0. So that doesn't always happen, obviously. That's just a really special case of what's going on here. So like I said, that's going to give us 0. And that's because sine and cosine are solutions to the differential equation of this portion of this. And that's because cosine and sine happen to be solutions to a differential equation that we would get if we were to leave off this minus 2y prime part. Okay, so anyway, now we need to impose this equals to cosine of x plus 3 times sine of x. Okay, so let's bring this down. We have minus 2, and then yp prime is minus a times sine of x plus b times cosine of x. And like I said, we need that to be equal to cosine of x plus 3 times sine of x. Now let's maybe underline this equation in pink, and what we want to do is extract the coefficients of sine and the coefficients of cosine from this equation. And that's using the fact that sine and cosine are linearly independent functions, which you can check with the Wronskian. Okay, so extracting the coefficient of sine from the left-hand side gives us 2 times a, and in the right-hand side we get 3. And then extracting the coefficient of cosine from the left-hand side gives us negative 2b, and on the right-hand side gives us 1. So we can easily solve that. We'll get a is equal to 3/2 and b is equal to negative 1/2. Now we can take those two values and plug them back into our general form of our yp, and we'll have our solution. So notice that y will be equal to yh plus yp, so that'll be our solution. The homogeneous part plus the particular part. So in our case, that'll be c1 plus c2x times e to the x. And then we'll have minus half cosine of x plus 3/2 times sine of x. And that would be our final solution to this differential equation. Okay, let's do another example. Okay, so our next example will be y double prime plus 3y prime plus 2y equals 20x plus 16 times cosine of x plus 10 times sine of x. So let's notice here we have a degree 1 polynomial, and here we have a constant which is a degree 0 polynomial. So that means for our guess, in order to ensure that it's as general as possible, we should have 2 degree 1 polynomials. So let's write those as maybe a1 sub x plus a0 times cosine of x plus b1 times x plus b sub 0 times sine of x. So that fits the mold of our format over here. So now we'll take a derivative and a second derivative, we'll plug that into our initial differential equation, and that'll help us fix a1 a naught and b1 b naught. Okay. So anyway, let's take yp prime. So taking the derivative of the polynomial part first will give us a1 times cosine of x, and then we'll have minus a1x plus a naught times sine of x. That's from taking the derivative of the cosine part. And then we'll have plus b1 times sine x, and then plus b1x plus b0 times cosine of x. Now let's collect the cosine terms and the sine terms just to keep it kind of like nicely organized. So let's see what we have for cosine terms. We have a1 here, and then we have b1x plus b0. So we'll have b1x plus a1 plus b0 times cosine of x. And then for the sine term, we'll have a minus a1x plus a naught minus b1 times sine x, where I have to change that sign because I factored a minus out. Okay, so that's where we are at the moment. Now let's take a second derivative, so yp double prime. So that's going to give us something like b1 times cosine of x from taking the derivative of the polynomial portion. And then we'll have minus b1x plus a1 plus b naught sine x from taking the derivative of the sine portion. And then we'll have minus a1 times sine x and minus a1x plus a naught minus b1 times cosine x. That's from taking the derivative of the cosine portion, or the sine portion. Now let's do the same thing that we did before and gather our sines and cosines. So let's see, gathering our cosines, we have a b1 here, and we have minus negative b1 here. So that's going to give us 2b1. But maybe putting that together, it would be more easily written as minus a1x plus a naught minus 2b1 times cosine of x. So something like that I think works nicely. Notice that I factored a minus sign out and that changed some signs. And then we'll have a minus sign here, and then the coefficient of sine will be, let's see, we'll have b1x plus 2 times a1 plus b naught times sine of x. Okay, so there we've got it. And now let's do our combination of yp double prime plus 3yp prime plus 2yp and see what we get. So we need something in front of cosine as well as something in front of sine. So that's going to be the tricky part here. Okay, so let's first look at the coefficient of x times cosine of x. So we get a negative a1 from this term. We get 2 a1s from this term. So that means we're going to have a positive a1 times x. And then we'll also have a 3 times b1 times x from this yp prime part. So we've got a1 plus 3 times b1 all times x. Okay, so like I said, that's our coefficient of x times cosine of x. Now let's see the coefficient of just cosine of x, so the constant times cosine of x. Let's maybe do a scratch calculation down here so we make sure not to make a mistake. So we'll have minus a naught plus 2b1. So that comes from our yp double prime, and then plus 3 times the coefficient from yp prime, so that's going to be a1 plus b0, and then plus 2 times a naught from the 2yp. Okay, and then let's just remember that this is the coefficient of cosine of x, not x cos x, but cosine of x. So let's see, this a naught and this 2a naught will cancel down to just an a naught. And then we'll have also plus 3b0, and then plus 3a1 plus 2b1. Great, so we've got that combination right there. So let's write that out. So we've got plus a naught plus 3b naught plus 3a1 plus 2b1, and then all of this is times cosine of x. So notice we have the coefficient of x cosine of x and the coefficient of cosine of x. Okay, so now let's calculate the coefficients for sine as well. Okay, so now let's calculate the coefficients for sine, starting with the coefficient for x times sine of x. So let's maybe put plus here, let's put big parentheses, and then we'll have a sine of x over here. So let's see, for x times sine of x, we'll get a minus b1 from this term, a minus 3a1 from this term, and then a plus 2b1 from this term. So in the end, that'll be minus 3a1 plus b1 times x. And look, this has a nice similar shape to what's going on right here, and that kind of makes sense just by the behavior of sine and cosine. Now let's look at the coefficient of just sine of x. And like we did before, we'll calculate that kind of over here to the side just so that we don't make a mistake. So from the yp double prime, we'll have minus 2a1 minus b naught. So that's from this coefficient of sine of x. From 3yp prime, we'll have minus 3a naught plus 3b naught. So that's from this guy right here and this guy right here. Sorry, that should be a b1. Okay, sick. And then multiplying this by 2, we'll get 2b0, so plus 2b0. Okay, so let's see what that simplifies to. So we've got minus 3a0 and then plus b0. So that's from this minus b0 plus 2b0. And then we'll have minus 2a1. And then finally, we will have 3 times b1. So let's write that in here. So we have minus 3a0 and then plus b0 minus 2a1. And then, like I said, plus 3b1. Now let's color code the equations which we'll start the next board with. So this right here is our coefficient of x times sine of x, but there's no coefficient of x times sine x in our differential equation. So we know that this must be equal to 0. Okay, so that's off to a good start. And then this right here, this a1 plus 3b1 x cosine of x must be equal to 20x cosine of x. So that means that number should be 20. Let's maybe underline that up here. Then this number right here, which is the coefficient of just cosine of x, must be equal to 16. And that's because of, well, I kind of over-underlined this thing right here. And then finally, all of this that I'm underlining in blue here has to be equal to 10. And that's because our coefficient of sine over here is 10. Okay, so like I said, let's start the next board with this system of equations which we'll solve in order to give us our final solution. So by assuming our particular solution had the following form, we gain the following system of 4 equations and 4 unknowns related to these coefficients. And I've color-coded them just as we had on the previous board with bullet points in this case. So let's notice that these two left equations only involve a1 and b1. So that's nice because that should allow us to simplify everything pretty quickly. Okay, so let's first notice that maybe we could take this second equation here and solve it for b1 pretty easily. So that gives us b1 equals 3 times a1. And then we can take that solution and plug it into our original equation. And that will leave us with something like a1 plus 9 times a1 equals 20. So in other words, a1 equals the number 2. So that's good. We've got a value for a1 immediately. Now let's see what we get for b1 based off of this. Oh, but look, b1 is 3 times a1, so that means b1 is the number 6. So immediately we have a1 and b1. But now we can transform these second two equations using these values for a1 and b1. So let's see what that'll leave us with. We'll have a0 plus 3b0 plus 3 times a1, so that'll be 6, plus 2 times b1, so that'll be 12, equals 16. And then we'll have minus 3a0 plus b0 minus 2 times a1, so that'll be minus 4, plus 3 times b1, so that'll be plus 18 equals 10. And this, just to bring the color coding down, that's our new version of our yellow dotted equation and our blue dotted equation. But now we can simplify this quite a bit. So notice 6 plus 12 is 18. So 6 plus 12 is 18. We can move that over and we get all of this is equal to -2. Great. And then 18 minus 4 is 14. We can move that over and we'll get -4. So that gives us a simpler set of equations to solve. Well, really, it's the same set of equations. And so from here, we would maybe want to do something like take this first equation and multiply it by 3. That'll leave us with 3a0 plus 9b0 equals -6. And from here, we can add these two equations. So if we add these two equations, the a zeros will cancel, and we'll be left with 10b0 equals negative 10, which means that b0 is equal to negative 1. And we've got a value for b naught. But now we can plug that in really anywhere we want and get a value for a naught. And at this point, I'll just tell you that a naught is equal to 1, as that's just the leftover calculation, which isn't so bad at all, which means we can finally write down a final form of our particular solution as 2x plus 1 times cosine of x plus 6x minus 1 times sine of x. And that would be, like I said, our particular solution for this differential equation. And then, well, what would the final solution be? Well, the final solution would be the particular part plus the homogeneous part. The homogeneous part we can get from methods from a previous video. So let's notice that the associated polynomial for the homogeneous differential equation will have roots of -1 and -2. So that means we know this is c1 e to the minus x plus c2 e to the minus 2x. So our final solution would be a sum of those two. Okay, so we've just done two examples that exhibit this first type. Now let's do an example exhibiting this second type. For our next example, let's look at the differential equation y double prime plus 4y equals 16x times sine of 2x. And this fits the mold of this second type down here because the homogeneous solution is of the form c1 cosine 2x plus c2 sine 2x, which you can check by methods from the previous video. So notice our forcing function here is 16x times sine 2x. So that means for our choice of the degree of polynomials a and b, we need 1 plus the maximum degree that we see here, which is 1. So that means we need to look at quadratic polynomials. So that motivates the following guess for our particular solution. So we have yp is equal to a2x squared plus a1x plus a naught times cosine of 2x, and then plus b2x squared plus b1x plus b naught times sine of 2x. And then immediately we can start getting rid of terms. And that's because this constant times cosine and this constant times sine will fulfill the homogeneous differential equation, which means when put into this left-hand side, they will cancel down to 0. So that means there's really no point in looking at these. So we can zero these things out immediately. And that's because we're going to essentially put them back in this form when we look at our final solution. They won't be parts of the particular solution. Okay, so now let's take our derivative on the path to taking our second derivative. So our first derivative will be 2a2x plus a1 times cos 2x, and then minus 2a2x squared plus a1x times sine of x. So like I said, that's our first part. And then the derivative of this second bit will be 2b2x plus b1 times sine of 2x, and then plus 2b2x squared plus b1x times cos of 2x. Make sure to not forget to put the 2x inside of the cosine and the sine. Okay, so now let's do the same thing as before and collect the cosine terms and the sine terms. So let's see. Let's first collect the cosine terms. We'll have 2b2x squared. That'll be our only x squared term. And then for the x term, we'll have 2b1 and 2a2. So there we'll have 2a2 plus 2b1 times x. And then our constant term only comes from this, so that'll be plus a1, and then we'll have cosine of 2x. Okay, great. Now let's also group the sine portions together. So we'll have minus 2a2x squared. So that's our x squared term. And then we'll have a plus a minus 2a1 plus 2b2x. So that'll be from this 2b2x and the a1x over there. And then finally plus b1 for our constant term, and then we'll have sine of 2x. Okay, so that's our first derivative. Now let's take our second derivative. So yp double prime. So again, we have to use the product rule. So that'll give us 4b2x plus 2a2 plus 2b1, and then cosine of 2x minus 2, and then the same polynomial. So that'll be 2b2x squared plus 2a2 plus 2b1x plus a1. Now we'll have sine of 2x. That's from taking the derivative of the cosine portion. Then taking the derivative of this, so that'll leave us with plus a minus 4a2x, and then minus 2a1 plus 2b2, and that's all attached to sine of 2x. And then taking the derivative of the sine portion will give us plus 2 times the same polynomial. So minus 2a2x squared plus minus 2a1 plus 2b2x plus b1, and that's all multiplied to cosine of 2x. So notice all we need is the original function and the second derivative. So let's rewrite the board with just those two parts and maybe with the second derivative sifted. So we won't do that calculation on screen. Okay, so after gathering everything together, this is what we have for yp double prime. So notice it's quite a bit of a mess. The coefficient of cosine 2x is minus 4a2x squared plus this minus 4a1 plus 8b2x plus 2a2 plus 4b1 cosine 2x. Then we've got a similarly complicated coefficient for sine 2x as well. And now our game will be just as before, so we'll impose this differential equation. So we'll have yp double prime plus 4 times yp. So we're going to have something in front of cosine 2x and then something in front of sine 2x as well. So notice the something in front of cosine 2x can be gotten from adding this to 4 times this. So notice the x squared terms will cancel, and then the a1 terms will cancel as well. So that's actually quite nice. And then we'll have 8b2 times x, and then we'll have this as well. So plus 2a2 plus 4b1, and then I can move this over cosine 2x. Great. So now let's do the coefficient of sine 2x as well. So here we'll have minus 4b2, and then we'll have a plus 4b2x squared as well. So that'll cancel. So that's actually pretty nice too. And furthermore, this 4b1 and this b1 will cancel as well, that coefficient of x. That'll leave us with minus 8a2 times x. Great, and then we've got no constant terms up here, so down here for our constant terms, we'll have minus 4a1 plus 2b2, and then this is going to be times sine of 2x. So we have something like that. And now we can equate coefficients just as before. So maybe I'll note that this is plus 0 times the cosine of 2x. So that tells us that everything here has to be equal to 0. So 8 times b2 must be equal to 0, and this combination of a2 and b1 also must be 0. We also get that negative a2 has to be equal to 16. That's because we have minus 8a2x times sine 2x, and we've got 16x sine 2x over here. Okay. And then we need this as well to be equal to 0 because that's not exhibited over here on the right-hand side of our differential equation. So let's note that that's by setting this thing equal to 16x times sine of 2x. So let's notice that immediately we see that a2 is equal to negative 2, and that's from this pink underline right here linking up with this pink underline over here. And now we can go through the rest. So if a2 is negative 2, plugged back up here, we'll see that b1 has to be equal to 1. So we've got that b1 is equal to 1. And then b2 is equal to 0 from this equation, so b2 is 0. And then finally from here we also see that a1 is equal to 0. So that gives us our final solution for our particular part, and that'll be minus 2x squared times the cosine of 2x, and then plus x times the sine of 2x. And of course we need to add that to our homogeneous part if we wanted a final solution. Okay, so now that we've done all types of examples from over here, let's look at a slightly more general case. So this will be our last example for the video, and we're not going to work through all of the details here. We'll get it to the point where it looks like one of our previous examples. And then since we did a couple of those, I think we're good to go. So here we've got the differential equation y double prime minus 3 times y prime plus 2 times y equals e to the minus 2x times 2 cosine 3x plus 150x minus 34 times sine of 3x. Notice that does not fulfill the setup to this theorem, but we can do a substitution in order to turn it into a differential equation which does fulfill the setup for this equation. And we'll do that by setting y equal to e to the minus 2x times z, where z is a new function. So notice that that means y prime is equal to, let's see, we'll have e to the minus 2x times z prime minus 2 e to the minus 2x times z, and then we'll have y double prime equals e to the minus 2x times z double prime minus 4 e to the minus 2x z prime, and then finally plus 4 e to the minus 2x times z. That's just from taking the derivative, being careful about all of our rules. Okay, so now if we plug all of these, so y, y prime, y double prime, into the original differential operator over here on the left-hand side, let's see what this transforms into. So we'll have y double prime, which is this bit. Well, actually, we can factor in e to the minus 2x out of the whole thing, so let's do that. And then we'll be left with z double prime minus 4z prime, and then plus 4z. That's our y double prime portion. And then we'll have minus 3z prime plus 6 times z. That's from the minus 3 times y prime portion. And then we'll have plus 2 times z. That's from this 2 times y portion. Okay, so let's see, that is going to give us e to the minus 2x, and then we'll have z double prime, and then collecting terms, we'll have minus 7z prime. And then let's see, 4 plus 2 plus 6 is 12, so plus 12z. And we have that's equal to this right-hand side of our differential equation. But notice we can multiply both sides by e to the 2x, and that'll cancel this exponential, leaving us with a differential equation for z. So we have z double prime minus 7z prime plus 12z is just equal to the polynomial trigonometric part. So that'll be 2 cosine of 3x, and then plus 150x minus 34 times sine of 3x. So using this transformation, we have achieved a differential equation that we can solve using this theorem, which of course we did some examples of that. So I won't go through all of the details. I think you've noticed that these are quite long and maybe not complicated, but strenuous. So I don't think we really need to see another one at the moment. But what I'll say is that the solution, or the particular part of the solution, ZP, is equal to 7x plus 1 times cosine of 3x, and then plus x minus 2 times sine of 3x. And that's for our function z. But that tells us that our solution y will be e to the minus 2x times this. So y is equal to e to the minus 2x times, I'll just write zp, where we bring that down. So that's condensing all of this into this term. And then of course we need the solution to the homogeneous part as well, but that'll be c1 e to the x plus c2 e to the 2x, just given the factorization of the component polynomial here. And that would be the final solution to this differential equation. So just to reiterate what we did a simple substitution. So y equals e to the minus 2x times z, where we gained the e to the minus 2x by looking at this. And that gave us the availability of this theorem, which we know how to work with. So we can always reduce this more general form into this specific form. Okay, I'm gonna leave you guys with some warm-ups. Okay, I'll leave you with 2 warm-up problems based on what we saw today. So the first is y double prime plus 3y prime plus 2y, or that should be just plus y, equals 2 minus 6x times cosine of x minus 9 sine of x. Then the other one also involves an exponential function. We've got y double prime minus 2y prime plus 5y equals e to the x times 8x plus 16 times cosine of 2x plus 6 minus 8x times sine 2x. And that's a good place to stop.